Good evening, everyone. I am Dr. Bharat Kesari Swain, and in the previous lecture, I discussed about the Laplace transform definition and its existence, and some examples whose Laplace transform does not exist, and also I discussed the applications of the Laplace transform. And today in this lecture I will discuss about some example how to find Laplace transform of some functions. So let's start. Okay, so first is Laplace transform of the exponential function e to the power at, and by the definition we have Laplace transform of f of t is integration from 0 to infinity e to the power minus st and f of t dt. And here, since we have f of t as e to the power at, so in place of f of t we wrote e to the power at. So 0 to infinity e to the power minus st e to the power at into dt. Now just we add the power, since the power of e is equal to minus st here and power of e is here 80. So we added these two and we write like this: 0 to infinity e to the power minus s minus a whole into t dt. Okay, and then just integrate as usual, because we know that exponential function, integration of exponential function is e to the power x, is again e to the power x, and if it is e to the power x, then it will be e to the power x by a. So that's why e to the power minus s of minus a whole into t and divided by a minus s, because minus of x minus a is a minus s and limit is 0 to infinity. So why we wrote like this? Because if I write like this, and then we can say this is a negative term, and after putting limit it may be e to the power minus infinity. So after, because these are the limit of t, so e to the power minus s is constant, so 1 by a minus s we take out, and the rest part is what? E to the power upper by putting the upper limit, it is e to the power minus infinity minus or lower limit, it is e to the power 0. And why it will be e to the power minus infinity? Because s greater than a, we consider it is as s minus a. So when s greater than a, then we will say that it is e to the power minus infinity. Is it okay? Now, so 1 by a minus s and e to the power minus infinity is 0, and e to the power 0 is 1, so 0 minus 1 and it will be minus 1, so by multiplying with this it will be 1 by s minus a. Is it good? So what we got? Laplace of e to the power at is equal to 1 by s minus a. And when it is 1 by s minus a, when we can say that Laplace of e to the power at is 1 by s minus a? When s greater than a. So this is the important part. If s greater than a, then we can say Laplace of e to the power at is equal to 1 by s minus a. So try to remember this so that we can apply this as a formula in the next example. Okay. Now, before going to the next example, we have to discuss that the linearity principle. What is the linearity principle? That linearity of Laplace transform. So what is this? Laplace transform is a linear operation. What does it mean? That is Laplace of a into f of t for any two function f and g, and a and b, small a and small b, these are some constant. So Laplace of a into f of t plus b into g of t will be equal to a into Laplace of f of t plus b into Laplace of g of t. That means we can operate the Laplace operator with f and g separately. We can prove this also. So what is the proof? Laplace of a into f of t plus b into g of t. We have to find this, is not it? And by definition we have, suppose this consider this as a whole function. This is because addition of two function is this, so another function is here. So Laplace of a into f of t plus b into g of t. So considering this whole addition as a function, as a function, so we can write that Laplace of f of t we have e to the power integration from 0 to infinity e to the power minus st f of t dt. So that's why we can write it as integration from 0 to infinity e to the power minus st, and in place of f of t here it is aft plus bf into g of t whole into dt. Now because a is constant, we can take this and it will be 0 to infinity e to the power minus st f of t, because we can separately integrate, because this is the addition of two functions and we know that integration is also a linear operation. So that's why we can write a into 0 to infinity e to the power minus st f of t dt, again plus b is again constant, and then into 0 to infinity e to the power minus st into g of t dt. And now if we consider the definition here, so by definition this term, what is this? A is constant, a, and this is the definition of Laplace transform of f of t. So that's why you can write this is Laplace of f of t plus b into, again this integration, what this integration is, what is this integration? Integration from 0 to infinity e to the power minus st, and in place of f of t it is g of t. So that's why you can write it as Laplace of g of t. Laplace of g of t. So a into Laplace of f of t plus b into Laplace of g of t. So Laplace of a of t plus b into g of t is equal to a into Laplace of f of t plus b into Laplace of g of t. So that's why Laplace transform is a linear operation. Understood? Okay. Now we will discuss Laplace of sin 80 and Laplace of cos 80. How to find these two Laplace transform. So to find these two Laplace transform, what we will need, that is Euler's formula, that is e to the power I theta, that is equal to cos theta plus I sin theta in complex case. And what is I here? I equal to root over of minus 1, and if you take its square, it will be I square equal to minus 1. So now if you consider Laplace of I80, so in place of theta here it is 80, so what we can write? Laplace of cos 80 plus I sin 80, is not it? Now since Laplace transform is a linearity, means it satisfy the linear principle, so that's why you can write Laplace of cos 80 plus I Laplace of sin 80. Now what we know that Laplace of e to the power I80, we have the formula Laplace of e to the power 80 equal to 1 by s minus a, and in place of a here it is ia. So Laplace of e to the power I80 equal to 1 by s minus ia, is not it? In place of a here it is ia, so that is 1 by s minus ia. And since it is means to separate the real and imaginary part, we can multiply its conjugate in numerator and denominator. So s plus ia and s plus ia we multiply in numerator as well as in the denominator. So what we got now? S plus ia divided by a square plus a square, because it is a plus b into a minus b, a square minus b square formula. So s plus ia divided by a square plus a square. Now we can separate the real part and imaginary part. So what the real part? S by a square plus a square plus I into a by a square plus a square. Okay. Now since it is real part and imaginary part, again what is this equal to? It is equal to Laplace of cos 80 plus I Laplace of sin 80. So this is complex number, it is also complex number. So these two complex number are equal, and when they will be equal? If and only if its real part will be equal to real part and imaginary part will be equal to imaginary part. So that's why Laplace of cos 80 equal to s by a square plus a square, and Laplace of sin 80 equal to a by a square plus a square. Okay, so we can remember these two formula. Laplace of cos at is a square plus a square plus a square, and Laplace of sin at is a by a square plus a square. Okay, so we have to remember this, and to solve the complicated problems of Laplace transform, this derivation is very important, and the formula is also important. Okay, so we have to remember this, is not it? Next question is Laplace of cos hyperbolic t and Laplace of sin hyperbolic t. By the definition, we know that cos hyperbolic t is e to the power at plus e to the power minus at by 2, and sin hyperbolic t is e to the power at minus e to the power minus at by 2. Okay, so directly you can find Laplace of cos hyperbolic t, that is Laplace of e to the power at plus e to the power minus at by 2. Directly put this formula, and using eliminative principle you can separate Laplace of e to the power at plus Laplace of e to the power minus at whole divided by 2. And directly you can put the formula also, because we know that Laplace of e to the power at is 1 by s minus a, so 1 by s minus a, and in place of a here it is minus a, so it will be 1 by s plus a. So if you add these two, it will be s by a square minus a square. So we can write Laplace of cos hyperbolic t is s by a square minus a square. Similarly, you can try yourself how to find this, and the result will be what? Laplace of sin hyperbolic t will be a by a square minus a square. So try yourself. Is it easy? Okay, guys. In the next lecture, we will discuss further property of Laplace transform, and with different examples also we will discuss in the next lecture. So thank you.